Okay, in this video we continue our discussion on projectile motion by considering what happens when we launch projectiles at angles, not just horizontally. So in this video we start to look at angled projectiles. If an object is launched at an initial angle theta naught with the horizontal, the analysis that we did before, very similar to what we're going to do now, it's just that we have an initial vertical velocity, and so we have to consider that rising and falling action of that projectile. So as you recall, anytime we have a velocity or any kind of vector that needs to be resolved, we simply use that the horizontal component, in this case v naught x, would just be v naught multiplied by the cosine of the launch angle, provided that angle is relative to the horizontal. And of course, v naught y would be v naught multiplied by the sine of that angle. Now, just as we saw before, the horizontal motion of this projectile stays constant throughout. There's nothing affecting that motion. So if I were to draw a dot diagram to look at what that projectile looks like horizontally, it looks something like this. Now, while it's also rising and falling, we can see that the y component is changing due to that acceleration due to gravity. So this is really just a combination of two different kinds of motion, a rising and falling, while it's also moving horizontally. And that's where we could trace out that nice parabolic arc as we've seen before. Now, when we go to solve projectile motion problems, particularly those in which we have some angled launch, it's important to follow sort of a nice process for us. Number one, always read the problem carefully. Make sure you know what you're asked for. Choose the objects that you're going to study. It's pretty much the projectile in these problems. Draw a diagram, usually a good starting point. Choose an origin and a coordinate system. If you call up positive, make sure you stay consistent with that. Decide on the time interval. Now, this is the time that it's the same in both directions, but it's only the time in which the object is moving with a constant acceleration g. If this is true projectile motion with no air resistance, then whenever it's in the air, it's accelerating only at the value of g. Examine the x and y motions separately. You may need to resolve velocity into its components. List the known and unknown. Remember, Vx doesn't change. There's nothing changing the motion in the horizontal direction. And sometimes we need to look at what's going on at the highest point. Remember, Vy is 0 up there. Plan how you're going to proceed. Use the appropriate equations. You may need to combine some of them. Now, in this video, I'm going to show you two examples. Both of these are somewhat involved because of the vector resolution. There's a later video in which I will show you something called the level range formula that can be used at times. It could actually be used for this problem, but I'd like to show you how we could solve this one using vector components. Here we have a student egg launch device. Perhaps you've already done your egg launcher device in our class. It launches an egg from the ground at a velocity of 25 meters per second at an angle of 47 degrees from the horizontal. And I see right now that this one is from your textbook that said 37. Let's go ahead and just change that to 47 so that we don't have any confusion. So a 47 degree launch angle. We want to answer a variety of questions. What's the maximum height of the egg, the time to reach the apex, the time to reach the ground, and how far away it's going to hit the ground. We want to know what the velocity vector is at the apex, the acceleration vector at the apex, and the acceleration vector halfway up. Let's go ahead and start looking at these first four problems. These are going to require some computation. Now, to help with the understanding here, I'm going to talk about each one of these things separately, and then I'll show you the work. The max height is dependent only on the vertical velocity, so we're going to use the UAM equations with the vertical velocity only. Same thing with the time to the apex. The time that's in the air, how high it rises, is dependent on how fast it's moving vertically. Symmetry can be used to find the time to the ground, once I know that time. And then how far? Well, how far it travels horizontally certainly depends on how long it's in the air, but it also depends heavily on how fast it's moving across the ground. So we're going to break this up into components, and then we're going to go ahead and apply the UAM equations to each one separately, linking them through that time variable. So let's go ahead and take a look at this diagram. We already have the diagram shown here as an initial velocity of 47 degree angle. Well, our first step is to resolve that velocity into its two components. So let's go ahead and put a red arrow here to represent the v naught x, and let's put a blue arrow here to represent v naught y. Now I've already computed those. I have those off to the side, and so let's go ahead and put that one there. V naught multiplied by the cosine of that angle would give me 17 meters per second. And if I take V naught and multiply that by the sine of that angle, I get 18.3. Let's go ahead and handle these one at a time. So the maximum height of the egg, let's try with this one right here. we see that the maximum height depends only on the vertical velocity. And we've used this equation numerous times. V naught, sorry, let's try that again. V squared is equal to V naught squared plus 2a delta x. Now, we've seen delta x before, but this is vertical motion, so let's go ahead and just change that to delta y. Instead of calling this a, it's a very special a. This is an acceleration due to gravity, so I'm going to replace that with a g. And very importantly, we're only looking at a vertical motion, so I'm going to go ahead and say that that's v naught in the y direction. And since I'm looking for the maximum height, I know that when it gets up here, it stopped moving. So I'm going to go ahead, it stopped moving vertically, I should say. I'm going to go ahead and set that equal to 0, since that is the y velocity. All right, let's go ahead and solve this for delta y max. So just a little bit of algebra, and we'll be there. So delta y max equal to a negative v naught y squared all over 2g. And let's go ahead and start plugging in some of those numbers. That'd be a negative of 18.3. I'm going to drop my units there, please forgive. Let's square that, and I'm going to divide that by 2. Remember, I'm calling upward positive, so g will go in as a negative 9.8. And when I'm done, my trusty calculator can give me that answer. So 18.3 squared, divide that by 19.6, and I see that that's about 17.1 meters. Let's just call that, let's go 17.1. Now, if you've already done our egg launcher project, you know that we had to get it up to at least a 5-meter height. This would certainly have gotten there. What's the time to the apex? Again, time is dependent on the vertical velocity, so let's go ahead and try that one here. We've used this equation before. V is equal to V naught plus acceleration times time. We're going to be looking at the acceleration due to gravity. So I'm going to go ahead and use this equation. V naught would be V naught in the y direction. I'm looking for time to the apex. And we know that V in the y up there at the very top is 0. Let's go ahead and solve that again for time to the apex. So t would be equal to a negative V naught y all over g, and just like we did before, we have that negative 18.3, and divide that by negative 9.8, and we get for that just about 1.87 seconds. Now, time to the apex. Well, using ideas of symmetry, if it takes that long for it to rise, it's going to take the exact same amount of time for it to fall. So time back down to the ground would just be twice that. So we just simply multiply that by 2. And you see that that's about 3.73 seconds. Now, we're at the point where we can start to analyze how far it's going to travel. We've gone through the process of vector resolution, so let's go ahead now and take the time that's in the air, 3.73 seconds, and just consider how far it has moved horizontally at that constant rate. We see that it's moving horizontally at 17 meters per second. If it's in the air for 3.73 seconds, it really becomes a fairly simple calculation. Delta x, using a UAM equation, is just V naught in the x times time. There's no acceleration that way. So now we just go ahead and multiply those numbers together. So 17 meters per second multiplied by 3.73 seconds, and we get for that about 63 meters, maybe 63.4. And we have now how far it travels horizontally. Somewhat involved to do that with vector components. We could certainly do this problem more easily with something called the level range formula, but we can always use vector resolution. No problem with doing that, just sometimes a little bit more tedious. Now, what's the velocity vector at the apex? Well, at the very top of its motion, it hasn't stopped moving. We've already considered just rising and falling objects, and we know at the very top of motion, those objects have stopped moving, but here it's still moving at the initial horizontal velocity. So its vertical velocity, its velocity vector at the apex would just be v naught x, and that would be 17 meters per second. How about the acceleration vector at the apex? Well, the only way we can use projectile motion equations for UAM is if the acceleration is constant. And so the acceleration vector up there would just be g, 9.8 meters per second downward. What about halfway up? Well, halfway up, we have the exact same acceleration vector. Right? It should be the same throughout. And so that would be the velocity vector at the apex, the acceleration vector at the apex, and the acceleration vector halfway up. Let's go ahead and take a look at the next problem. Here we have a human cannonball shot out of a cannon 42 degrees from the horizontal with an initial speed of 25 meters per second. Perhaps you'd like to try that activity somewhere in the future. That seems like a lot of fun. A net is positioned at a horizontal distance of 50 meters from the cannon. At what height above the cannon should the net be placed in order to catch that human cannonball? And I have a picture hidden here. Let's take a look at it. And so here it looks like something out of a carnival. We have a person being shot out through here. You see a nice little strobe diagram showing the position of that person throughout the air. And you see they do a little flip here to be able to land safely in that net. So we have a set distance away for our problem. It's 50 meters. And for this one, just to show you how we might apply the principle of vector resolution to projectile motion problems, we're going to try to determine the height of that net to make sure that we catch him safely midair. Let's go ahead and take that picture mostly away, and let's start with a little diagram. So we have a nice little V naught there. Let's see, 25 meters per second at 42 degrees. I have vector components. We always, again, would be wise to resolve that right into its vertical and horizontal components. And I have a net drawn over here too. The net is located a distance 50 meters away. Let's go ahead and put a little arrow on there indicating that. And choose red since that's the horizontal direction. And so that's 50 meters. And in this case here, our goal is to figure out how high up it should be to catch him midair. So let's go ahead and switch it over to blue. I'd like to know that height. Okay, so that's our final answer is that one. So let's see how we're going to do that. We know enough information about its horizontal motion to determine how long he will be in the air. So if I want to, again, visualize this motion horizontally as a constant speed motion, just showing those little dots there. If we could figure out how long it takes for him to travel rightward, 50 meters, then we also know how long it takes for him to rise and fall. And so our goal here is to link those two things together. Let's start with the red. Very simple motion in the red. There's no accelerated motion. So delta x is just v naught in the x times time. And I'm looking for that time here. So let's just go ahead and take a delta x over v naught x. And let's see, 50 meters divided by 18.6 meters per second. And I'm, again, have to drop my units because of the difficulty of writing there. But we see that that's about 2.7 seconds. I'm going to try writing right on the screen here. 2.7 seconds. Has to be rather large, but that's okay. This is not too involved in the problem. So 2.7 seconds for him to get to that net horizontally. Let's go ahead and switch it over to blue. What I'd like to do is just figure out how high up he is at that point. So we've certainly used this equation before as well. We're considering vertical motion, so we're going to replace a with g, and we're looking at just velocity in the y direction. So we don't have to do anything with this equation, just plug these numbers in. He started moving vertically at 16.7 meters per second. He's in the air for that 2.7 seconds. Now, let's see, plus 1/2, I'm going to say minus 4.9 to take into account the direction of that acceleration, and then times 2.7 squared. And so now we can just go ahead and compute that. And it's not too bad, just sort of pay attention to the negatives and so forth where you need to. And I compute that to be about 9.4 meters. Okay, and so placing the net at a height of 9.4 meters would certainly be sufficient to catch him in that net. So there we go. A couple of problems for you on how we might use vector resolution to solve projectile problems in which we have an initial launch velocity that is, or launch angle that is not horizontal. Now, in the next video that you might watch here, I developed something called the level range formula. And the level range formula can be used on problems like this one here, where there's no elevation change. It cannot be used on a problem where we have an elevation change from beginning to end. So you have to know the limits of what equations can be used when, and we can always use vector components, but sometimes there's easier ways. And that will be the subject of the next video. That completes this one.